and thanks to Elizabeth for setting up for this talk very well by giving a lot of the definitions I will use. So in many ways, this is maybe a parallel story to what Elizabeth told us about. Before I start, I'll say that this is work in progress. It will be in the archive soon, hopefully, but it's not there yet. And it's joint work with these people. So it's Elisenda, it's Paul Helmich, it's MoRN, Benjamin Schröter, and Mate. Okay. And the starting point is the same as what Elizabeth told us about. So we have a chemical reaction networks that we can maybe consider with mass action kinetics. And the steady states will be given by a certain parametric polynomial system that looks something like this in this case. So there are some equations, some polynomials that come from setting derivatives equal to 0. That's the nonlinear part, and then there's a linear part that comes from certain conservation relations. In this case, there is only one, but there could be several. And the parameters that I mean when I say that this is parametric are the rate constants and the total amounts. So this K's and this C's. And a very basic question you can ask about this system is how many solutions are there? And in particular, if we care about positive steady states, then we ask how many positive real solutions does this system have if we plug in some values of the K's and the C's. Okay, that's the question that we're sort of trying to address in this talk. And yes, I say positive. So this goes back to the question that I think Tung asked to Elizabeth. What about boundary steady states? Some of the techniques that I will talk about here do also work for the boundary steady states, but the story will be more complicated. So I'll sort of hide that a little bit from you today. The simple answer could be that in principle, we could address the boundary steady states on a case-by-case basis. So if we want to consider boundary steady states where maybe species X1 has gone extinct, then we just try and see what happens if we plug in X1 is equal to 0. Then we get a new system that we can solve. And we do this for all possible combinations. This is, of course, a lot of different combinations to investigate. So it would be nice if some of this theory extended to also boundary steady states, but and partly it does, but it's a little bit more complicated. Okay, but how do we do this? Well, the dynamical systems answer to this would maybe be, well, let's just plug in some different initial values and solve the ODEs that Elizabeth showed us. That's certainly possible. Maybe the slight downside is that you would only find stable steady states. Maybe those are the most important ones from an applied point of view, but also the unstable ones, I think, I would argue that those are also interesting because they paint sort of a picture of the overall dynamics of the system. So having a grasp of also the unstable ones would be nice, and you can't see them by just solving the ODE. And also you would have to do a lot of different initializations, and there would be no way of knowing when you're done, when you have found all positive steady states. So another option, maybe the more algebraic option that I will try to sell you today, is to take a detour via the complex numbers and try to solve the system over the non-zero complex numbers with a tool called numerical algebraic geometry that I really enjoy working with. And in addition to this, you can then certify that you have found all solutions. And at the very end, you can filter out only the positive ones and thus answer our original question about positive steady states. Okay, that's the sort of the method I will try to describe today. And except from explaining how it works, I will also try to explain why the steady state degree that Elizabeth told us about, why that's relevant for this story, and also something about why tropical geometry can be of help. Okay, that's the plan for the talk. So let's start with explaining how numerical algebraic geometry works. So this will be very simplified and short, of course, but just to give you a sense of what we're doing here. So the idea is that we have a system, in this case, our steady state system that we want to solve with n variables, and there are n polynomials. And we want to find the roots over say, the non-zero complex numbers. Well, what you do then is that you take another system that's simpler to solve, and which you know has at least as many solutions as your original system, as your target system. Okay, we call this the start system. Then we solve this, and then we imagine a deformation, like a continuous deformation from the simpler start system to the more complicated target system. In fancy language, this is called a homotopy. You could do something. There are lots of different possibilities, but you could do something like this. It's called a straight line homotopy. We throw in a random number gamma here just to avoid hitting this discriminant that Elizabeth mentioned. And we see here that if we plug in t is equal to 0, we get g, so we get the start system. And when we plug in t is equal to 1, we get the target system. Okay, so that would be a smooth deformation. And then the trick is that you take all the solutions that you found of the start system and you trace them along this homotopy. It corresponds to solving a certain differential equation. Okay, this is called the Davydenko system. And that will give you a path from the roots of the easy start system to the complicated target system. Okay, visually it could look something like this. So here we have t is equal to 0. We have solutions of the start system. Of course, this really is, I've drawn it just as a line, but this is really happening in n-dimensional space. And we sort of imagine that we trace all the solutions of the start system to solutions of our target system. And if we have made sure that we had at least as many solutions of the start system as we want in the target system, and if we make sure that this homotopy is random enough, then there is a result called the parameter continuation theorem that guarantees that with probability 1, we will find all the solutions of the target system in this way. Okay, and but it's really crucial then that we a priori have some sort of grasp of how many solutions there should be of the target system. Okay, and that's where the steady state degree comes into the picture, because in some sense that's the best possible bound that you can find. Okay, and this has been implemented, so you can do various variations of this approach. In Julia, there is a package called homotopy continuation, but there's also Bertini, PHC pack, and many more implementations. So there are really like good ways of doing this in practice. It's not just a theoretical approach. Okay, that's numerical algebraic geometry. I said something about certification, so let me just explain that a little bit more clearly. So the idea is that once you've done this, you have a bunch of approximate roots of your system. Okay, but you want to say something about the true roots, ideally, and certification allows you to go from these approximate roots so for each approximate root, you get a box, so a product of intervals in n-dimensional space, where you can prove with interval arithmetic and the Banach fixed point theorem that there actually must be a unique true root. So you go from these approximate roots to slightly enlarged boxes where you know that there is precisely one true root. This has been implemented also, at least in the Julia package, where it's possible to use it since 2020 due to a very nice implementation by Briding, Rosa, and Tima. And just to, yeah, and how can you use this to actually say something about realness and so on? Well, if we just think about this for a while, so we imagine that we have one of these boxes, and you have something that looks like a real solution. Well, if this box is symmetric with respect to complex conjugation, then there is no other possibility than that whatever true solutions exist in here, that true solution needs to be real, because the complex conjugate of this real solution would have to be in some box, and that box would be the same as this if we have the symmetry, and due to the uniqueness, the complex conjugate of the true solution needs to be equal to the true solution, and then it's real. So that's something we can do. If in addition you can see that this box doesn't have any entries with negative real part, then that means that your solution, the true solution that exists in the box, must be positive. Okay, and by using similar arguments, you can also prove that a true solution can be non-real or that it's non-positive. So you can do this type of very simple analysis on all the boxes that you find for all your approximate roots, and thereby sort of partition them into different classes: so real solutions, positive solutions, non-real solutions, and non-positive solutions. And in particular, that means that we can filter out the positive ones and remove all the others. Okay. And finally, what you can do is that if you know a priori that your system can have at most n roots, where n would typically be the steady state degree that we heard about before, then, and if in addition we have seen that we have that many disjoint boxes, then by the existence and uniqueness that comes from certification, we know for sure, provably, that we have found all solutions. So we would have a guarantee that we haven't missed any solutions. Okay. I said before that by the parameter continuation theorem, we expect that we'll find all solutions with probability 1. But if we do go through all of this, and if we see that we have as many solutions as we expected, we would know for sure, not just with probability 1, but we would know for sure that we have found all solutions. Okay, so that's somehow the power of certification. And just to give you a very simple example, suppose that we try to solve this univariate polynomial. Okay, and that these are the approximations that come out. It certainly looks like this one is very, very close to being real. But how do we know for sure? Well, let's check the boxes. So we apply the certification algorithm, and we get boxes that look something like this. Okay. In practice, these boxes would be extremely tiny. Like usually this epsilon has order of magnitude 10 to the minus 13 maybe. But here I've drawn the boxes a little bit bigger so that we can actually see them. Okay, and then we see that this box is symmetric with respect to complex conjugation. And then we conclude that this solution that it corresponds to must actually be real. Okay, and these boxes, all points in those boxes have non-zero imaginary parts. So we conclude that these are non-real solutions. Okay, so here we would conclude that we have found one positive real solution. And since the degree of this univariate polynomial is 3, we know that sort of the expected number of solutions is 3. We have found 3 solutions, so we know that we haven't missed any solution. And then we can conclude that this is indeed the unique positive real solution. We have found all positive real solutions. Okay, so that's a very simple example of what you can do with this technique. Okay, let me move on and just explain again what the steady state degree is. The only difference really compared to what Elizabeth told us about is that I work with over the non-zero complex numbers, right? Because I don't want to bother with these boundary steady states. But other than that, it's the same. So the steady state degree is the maximum number of complex of roots over the non-zero complex numbers, and equivalently, it's also the generic number. That's also something that Elizabeth explained to us, that the steady state degree is what happens if we plug in generic values of the random of the parameters. Okay, and the reason that this works is somehow that over the complex numbers things are much easier than over the real numbers. Over the real numbers, parameter space, so this would be the space of the k's and c's, is partitioned into different cells where you have different number of roots in different cells. But over the nons, and then there is a discriminant that sort of divides parameter space into these cells. That would be these things. That would be the discriminant. But over the complex numbers, there is still the discriminant, but everything except the discriminant has the same number of complex roots. And that will be the steady state degree in this case. Okay, so that's what we mean with the steady state degree. And how do we compute the steady state degree? That's a little bit complicated. It's in general a hard problem to find the generic number of complex solutions of a parametric polynomial system. But what people have tried to do with the steady state degree before is to use something called Gröbner basis. It's a technique from computational algebraic geometry. So that's was done in 2016 for this wind pathway that Elizabeth showed us. It turned out to be 9. In general, this is a very heavy computation. So this can't be done for much bigger networks than that. For the n-site phosphorylation, just like Elizabeth told us, Wang and Sontag were able to sort of deduce a certain univariate polynomial of degree 2n plus 1, and from that we can deduce that the steady state degree must be 2n plus 1. We can use the mixed volume. Sometimes it is sharp, a sharp bound for the steady state degree, as Elizabeth explained. And this has been done for the ERIC model, for example, where it turns out to be 7. But in general, these are methods that don't. I mean, Gröbner bases always work, but it can be an extremely heavy computation. Um, and what people are mostly focused on is the mixed volume. And it relies on this Bernstein's theorem that we heard about before, which says that if we have a system where all coefficients are free and independent from each other, then the generic root count over the non-zero complex numbers is the mixed volume. But just like we heard, for our models, that's typically not the case. We have dependencies between the coefficients, and therefore this is only an upper bound. If we go back to this small toy example I showed you in the beginning, we see that the mixed volume would correspond to the generic root count when we have completely free and independent coefficients. But since our coefficients are not free and independent, let's say K3 and K4, K3 is repeated here, K4 is repeated here, and here we have even fixed coefficients equal to 1. So this is in general just an upper bound, and we'll see later in the talk that the steady state degree is 2 in this case. So significantly smaller than the mixed volume. Okay. The main sort of takeaway of this talk is that it turns out that we can compute the generic root count in another way that doesn't rely on Gröbner basis and that is generally much faster, and is as a tropical intersection number. Okay, which in some sense is a generalization of the mixed volume that we heard about before. Okay, that's the main result. And before I go into that, I think it's in order with maybe a quick crash course on tropical geometry. Before I do that, I can just quickly say that these numbers come out to be 56 for the wind pathway. But as Elizabeth showed us, it's actually 9. With the Gröbner basis computation, this takes 8 hours or more, and tropically it goes with just 15 seconds. So at least for this system, it's a bit of progress. Okay, so yeah, so what is tropical geometry? Let me just quickly explain what the idea is. So you take the idea is to go from the curvy and complicated world of algebraic geometry to the piecewise linear world of polyhedral geometry. And you do that by just changing the arithmetic operations in your polynomials from plus and times to minimum and normal plus. You also have to change what it means for a polynomial to vanish. So if you have a polynomial that looks something like this, you change the operations so that you get a minimization problem. You have to maybe turn the coefficients into, maybe have to turn them into, apply a certain valuation of the field. This is a technicality that you don't have to worry about. But the point is that polynomials become minimization problems, and we say that this minimization problem vanishes at the point if the minimum is attained twice. Okay, and the idea is that when you do this process of tropicalization, a lot of the geometric information about your varieties is retained. So here we have an elliptic curve of degree 3, and we can see that degree is 3 because we have these 3 lines emerging in different directions. We can see that the genus of the curve is 1 because we have a genus 1 thing here. So, and these are not coincidences. Like this is designed to retain geometric information. And the point is that also root counts are retained in certain settings. Let me also just explain how you count intersection points tropically. You have to be a little bit careful. For example, here we have a blue curve and a red curve that we have intersected, and we only count these intersection points even if there are infinitely many points in the overlap between them. And it's because those points that we don't count are not stable under perturbations. So if we just perturb the curves a little bit in relation to each other, we see that we only have 1, 2, 3, 4 points. And it's only those 4 points here that correspond to those 4 points here that we count. That's somehow the idea of stable intersection. Okay, with that being said, let's look at how we actually do the tropicalization. In general, doing tropicalizations is a very hard problem, but here we are able to use a little trick that allows us to do it much more easily. So we just re-embed our system into higher ambient dimensional space. So higher dimensional ambient space, where we just introduce a new variable for each monomial that appears in the system. So for this monomial, we introduce a new variable z1. For this, we introduce a new monomial z2, a new variable z2, and so on. And this turns our system into a system of binomials. And then we are left with some linear equations corresponding to the original equations and some linear equations that come from the conservation law. So we split the system into 3 parts. And I think there is a typo here. So I think these x3s shouldn't be there. Sorry about that. But yeah, we have a binomial system, and tropicalizing binomial things is easy. We just get something linear. And when we tropicalize these linear things, well, we get something more complicated, but it boils down to a matroid theoretic computation of a Bergman fan. If you don't know what this word means, it's not so bad, but these are just combinatorial things that are quite easy to compute. There are well-known algorithms for how to do this. Okay, and thanks to the special structure of reaction network systems, each parameter here, it always appears together with the same new variable z, and that gives us something called tropical equivariance over the field of Poisson series. Again, this is a technicality that's not so important, but the point is that there is a special feature of the reaction network theoretic system that we're using here, namely that each parameter up here always appears with the same monomial. Therefore, they always appear with the same new variable down in the modified system, and that turns out to be crucial. Okay, so we do these computations. This is quite heavy. This is very fast. We do the intersections. We have to be a little bit careful about multiplicity, but at the end of the day, it turns out that the steady state degree that we wanted all along is just the number of intersection points between these objects. In addition to this, we get an explicit description of these homotopies that we should use and what start system we should use to actually find these points. Again, this is a little bit technical. I won't go into it, but it turns out that for each point in the stable intersection, we can construct an explicit homotopy. When we plug in t is equal to 0, we get the start system that is binomial. Binomial equations are easy to solve, much easier than any other polynomial system at least. And there will be precisely as many solutions as the multiplicity of this point that we find. So if we do this for all points, we get several start systems, and in total they will trace out exactly the steady state degree number of paths. So in that sense, we find a way to solve our system optimally without any superfluous paths. Okay. In the remaining minutes, I'll explain maybe a slight subtlety, and that is like how do we deal with this heavy computation? Because that's really what's limiting us. This 15 seconds that we had for the wind pathway are almost exclusively spent here. Okay, and for bigger systems, this starts to become a problem. And that leads us to the concept of transversal matroids. So it turns out that if these matroids have a certain combinatorial property called transversality, then the steady state degree will go from being just a mixed, a tropical intersection number to actually being a mixed volume. Not the same mixed volume as the one we started with and that we tried to improve, but another mixed volume. And this mixed volume will come from a new system that we get from a certain so-called transversal presentation. So just to maybe it's easier to see this in an example. So for the running example, the small toy example I showed in the beginning, the linear parts came out to be these two. Okay, and it turns out that the matroid that we get if we look at the columns of the coefficient matrix, so that's the central matroid that governs the tropicalization. Well, it turns out that, and the matroid just records the sort of which columns are linearly dependent. And it turns out that that data is the same for this matrix, where we have replaced where now all non-zero entries are completely independent parameters, alphas. That's what it means for this matrix to be transversal. And since now all parameters and let's say all coefficients in this matrix are independent parameters, we will end up with a mixed volume. So we will suddenly be in the setting of Bernstein's theorem, and it will turn out that the steady state degree of our original system will be the mixed volume of this modified system, where we have these binomials and we have these linear things that come from this transversal presentation. Okay, this is somewhat of a technical construction, and you don't need to understand the details, but the point is that sometimes the steady state degree comes out to be a mixed volume, and in that case, it's much faster to compute. Okay, just to give you an example, if we do this for the n-site phosphorylation family that we heard about before, it turns out that we always have a transversal matroid, and we actually have a certain like we have an explicit construction that gives us the transversal presentation. So in particular, we have a way to construct this new system for which that will have the same steady state degree, and it will be the mixed volume of this new system. Okay, so we have been able to make that construction, and it turns out to speed up computations a lot. So this becomes very infeasible already for n is equal to 3 to do with the classical Grosvenor basis technique. If we try to use our tropical intersection algorithm out of the box, we are able to do this at least up to n is equal to 4, but then it starts to become quite difficult. But if we do it with this transversality and turn it into a mixed volume, then it's easy to compute well up until, I think, n is equal to 7, and possibly it's feasible a little bit further than that. So this has the potential to speed up computations a lot if we have a transversal matroid, which is not at all always the case. For the wind pathway, for example, there we don't have this nice property. So there we're sort of stuck with these 15 seconds and can't improve that. Okay, I think this is a good time to just wrap up. So what we've talked about now is the steady state degree, which is the numeric number of solutions to the state equations over the non-zero complex numbers. Okay, this is a bound for the number of positive real solutions, but further, even more, it's useful if we want to find these positive solutions, because it tells us how to do numerical algebraic geometry with an optimal start system. And since we then also know how many solutions we expect, we can certify that we haven't missed any solutions, so that we have actually found all of them, and that's quite nice. Okay, we saw that since we have dependencies between the coefficients, so for example, this one are repeated, this one and this one are repeated, and this one are fixed, the steady state degree might very well be much smaller than the mixed volume. That's also something we saw in Elizabeth's talk. But we can compute it through a tropical intersection number, where the main idea was that we split the system into several pieces, a binomial part and some linear parts that are individually easy to tropicalize. And in a lot of cases, not all, but in a lot of cases, we are lucky that we have a transversal matroid, and then tropicalizing these things is very easy. And the steady state degree turns out to be a mixed volume, which is fast to compute, much faster than this. But it will not necessarily be the mixed volume of the original system. Okay, and additionally, this method gives us explicit start systems, explicit homotopy, so that we can actually carry out the numerical algebraic geometry solution. Okay, so what can we do in the future? Well, what we're looking into right now is that we're trying to do this for these particularly nice networks that Elizabeth told us about that are toric, where the steady states form a toric variety, because then we can tropicalize immediately without doing this trick of introducing new variables, and that means that we don't have to go into such a high-dimensional ambient space, and then it's a little bit faster to do the calculations. Okay, and another question that is very interesting and that we're trying to understand is, when are the steady state degree and the mixed volume of the original system the same number? Like when is the mixed volume actually a sharp bound of the steady state degree? Elizabeth showed us some examples where they are the same, some examples where the mixed volume is a terrible overestimation. And if we look in databases of realistic networks, such as the ODE base, it turns out that approximately it's half. So in half of the cases of these realistic networks, these are the same, which is quite a lot. And it would be interesting to understand better, like why are they the same? Is there a way to check this a priori so that we don't have to bother with all these tropical intersection number computations? Okay, that's all I have to say. Thanks a lot for your attention.